Alright folks, in this video I'm going to talk about data storage on your computer and analog to digital converters. In the book chapter, it talks about converting from decimal notation to binary, and then it talks about analog to digital converters. I'm going to talk about analog to digital converters first, and then talk about binary. So in this video I'm just going to talk about ADCs, analog digital converters, ADCs. And I'm going to point out a lot about things about bits and binary and things like that, but I'm going to explain it in such a way where we're really just talking about data storage and how computers store numbers. So if you look over here, right, if you just think about your computer, you've got your CPU, your central processing unit, that is, executing commands and things like that, talking to your hard drive, talking to your RAM, which stores numbers. And there's also this I/O, this input-output, where your sensors are hooked up to some sort of I/O device that is writing, to your CPU, potentially talking to your RAM and your hard drive. Now the sensors, if you have an analog sensor that's outputting a voltage or a current or something like that, it's going to be sending some analog signal. Now this I/O device, unless I've never seen it, so this I/O device needs some sort of way to convert that analog signal into a digital signal. And so, in my class, I have the students purchase a circuit playground. It's kind of like an Arduino. And that Arduino or that circuit playground has an analog digital converter, an ADC on board. So you can hook an analog signal to that Arduino or circuit playground, and its ADC will convert to digital so that you can store the numbers on your computer. If you hook up your mouse to your computer USB, your mouse has a lot of analog circuitry in there, like the optical mouse that's like figuring out where you are, but it's converting all of that to a digital signal before it sends it through USB. And so this is something that I think a lot of us take for granted because we just plug in USB and we're good to go. So let's talk about what I mean by analog and digital signals. So an analog signal is basically a signal that is something that I call continuous. It can be any number from minus infinity to infinity, assuming you have enough power. And so you can have 0 volts, 0.01 volts, 0.0001 volts, 1.25 volts, whatever. You can have any voltage in the real number line in here. And so that's why I drew this crazy squiggly line. Now, if you take this continuous signal and convert it to a digital signal, you're not going to get a smooth signal. You're going to get discrete jumps. Because a computer cannot store a continuous number. We live in a world where computers have so much storage, it looks like it's continuous. Like even this video camera, right? It's shooting at a frame rate that's high enough to trick our brains into thinking that it's actually a continuous amount of information, when in reality it's a discrete number of frames. Unless you're watching this, I don't know what I'm filming at, 30 frames per second, 60 frames per second, but you're getting a discrete number of frames back to back to back that is hitting your eyeballs so quickly it makes it look like it's continuous. Back in the day, I don't know if you guys have ever played on like the original Nintendo, that was an 8-bit computer, right? You only had so many pieces of information that you could store things, and so the amount of information that you could store was a lot less, and so people had to worry about these things when they converted from the continuous signal to this like staircase discrete signal. And like I said, nowadays you have so many pieces of information that it looks smooth, but if you zoom in far enough, you'll get to a point where you'll see the discrete nature. So I mentioned this already in passing. How do computers store information? Well, with a bit. And a bit can be a 0 or a 1. And the reason why computers like 0 and 1 is because 0 means off and 1 means on. Typically, like TTL logic, what it will do is they'll say, if I receive a voltage of a 0, I assume that's 0. Anything above some threshold, I'm going to assume that's a 1. And so if you're doing like a 3.3 volt logic, I think it's like around anything over 2.5 volts is considered on. And then you've got a 5 volt logic where it needs to be a little bit higher. So I think Arduinos operate on 5 volt logic. So a zero voltage to some sort of circuitry component is off, and then 5 volts to something it represents on. And so they basically take a continuous voltage signal from 0 to 5 volts and they bin it like a histogram into 0 and 5. And so you can either be 0 or you can be 5. You can be off or on, and that's it. If you're doing a circuit playground with 3.3 volt logic, you can either be 0 or 3.3 volts. You can be off or on, 0 or 1. If you have 1 bit, right, you can represent not necessarily 2 numbers, but 2 states. Okay? I can be off and I can be on. That's 2 states, right? If I have more bits, the more bits I have, the more storage I get, because I can represent more states. And what I mean by that is, think about your computers. Depending on when you're watching this video in this time period, right? Like when I was in college, everybody's computer was 32-bit. And then quite recently, I think it's pretty common for basically everybody's computer to be 64-bit. And what that means is that they have twice as much storage as they did before. And instead of having, like 1 bit, you can represent 2 states. Bits go in powers of 2. So if I have, 2 bits, I can represent 4 states. If I have 3 bits, I can represent 8 states, and then 16, and then 32, and then 64. And so if I have 32 bits, that's 2 to the power 32. That's a humongous number. Now computers are 64 bits, so that's 2 to the 64 power. That's a ginormous number. And so I was saying before that our computers nowadays have so many bits of information, we don't really see this staircase anymore. We see smooth, 4K HD images because there's just so many bits of information that we can store. And so I wanted to do an example here. So let's assume we have an ADC that's only 2 bits. So it's a 2-bit ADC. A 1-bit ADC, I can only represent 2 states, a 0 or a 1. But if I have 2 bits, I can be 0, 0, 0, 1, 1, 0, or 1, 1. I have permutations. If you guys remember from statistics, right? Like I've got 2 states, but I have 2 slots. So it's 2 times 2, which is 4. If I had 3 bits, I could be 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, and I could just do all the permutations on 1. I don't want to get into, this is binary, but I don't want to get into converting from decimal to binary. I just want you to think that in this case, I've got, 2 cards, and I can either flip them both face up, both face down, or I could be 1 face up, 1 face down, and 1 face down, 1 face up. So I can represent my system in 4 states. And so what I have here is I don't have states or numbers, I have 4 possibilities. There are 4 different possibilities that can be received to me. 0, 0, 0, 1, 1, 0, or 1, 1. And that's it, because I only have 2 bits. And so let's look at this analog signal. Let's say the voltage range of this ADC is 0 to 5. So I'm using an Arduino, I can hook up an analog sensor to it, and then analog sensor is going to output 0 volts, or it's going to output 5 volts, or anything in between. My computer, on the other hand, can't read that analog signal, so I'm going to discretize it into 4 different categories. Now, I'm going to lose information, right? Because, if I have a continuous variable, that means I have an infinite number of possibilities. And suddenly I'm taking my infinite number of possibilities and I'm shrinking it into 4 different possibilities. That's not fair. Imagine having, all of the colors in the world and then only being able to draw with 4 colors, right? That's essentially what you're doing. Versus the 64-bit computers now, you have 64 possibilities, right? I'm sorry, 2 to the 64 possibilities. So anyway, so this I drew in green. I tried to keep the color coding the same. So this analog signal can be any number between 0 and 5. And so it can be any number between 0 and 5, right? And so I'm drawing all of these tick marks here to basically represent that I can be any number in that space. But unfortunately, for my digital signal, I can only be these 4 states. And so what I'm going to do is I'm going to call those 4 states 0, 1, 2, and 3. I'm going to start at 0 because digital computers like to start at 0. C++ also like to start at 0. Python starts at 0. MATLAB's the only one that starts at 1. But, it's each his own. So I'm going to start at 0, 1, 2, and 3. And so basically those are my 4 numbers, right? I started at 0, ended at 3, but I have 4 numbers. 1, 2, 3, 4. So what I'm going to do is I'm going to say, okay, well, how big do I need to cut 0 to 5 to give me 4 discrete bins? And there's a pretty simple equation. If you take the upper range of the voltage minus the lower range of the voltage and divide it by 2 to the n, so that's going to be 5 minus 0 over 2 to the 2, which is 4, so 5 fourths. Every single bin of my histogram, if you will, is going to be 1.25 volts. And so that basically means if I receive an input signal that is anywhere between 0 to 1.25 volts, I'm going to give it a DO, a digital output of 0. Okay, that's not a voltage, it's the digital output. If I receive a signal that is between 1.25 and 2.5, I'm going to give that a digital output of 1. If I receive a signal between 2.5 and 3.75, I'm going to give it a digital output of 2. If I get a digital signal or an analog signal of 3.75 to 5, I'm going to give it a digital output of 3. And so, as an example, if I get a signal of 0.88 volts, that's going to be a digital output of 0. If I get a signal that's 2.9 volts, I'm going to give that a digital output of 2. Okay? Now, in order to convert that back to voltage, your digital output back to voltage, you need to multiply by this discretization. And so 0 times 1.25 is 0, 1 times 1.25 is 1.25, 2 times 1.25 is 2.5, 3 times 1.25 is 3.75. So you can see here there's a significant amount of error, right? If I get a signal that's 0.88, my computer is going to think it's 0 volts. That's an error of 0.88 volts. That's a lot, right? If I get a signal of 2.9 volts, I'm going to get a digital representation of 2.5. So my error is 0.4 there. So that's less than, but still, depending on what my input voltage is, in relation to the closeness of the next discretization on this ladder, I could potentially have a ton of error. And the reason why is because I only have 2 bits. So if you're programming an Arduino, or you're designing an Arduino or a circuit playground, are you going to put a 2-bit A to C on there? Absolutely not. And if you look it up, Arduinos have a 10-bit ADC. So that's 2 to the 10th power, which I think is 1024, I think. And so that means you have 1024 possibilities. So that means you're going to take 0 to 5 volts, and you're going to slice it into 1,000 little bins, which means you're going to be a heck of a lot more accurate. Now, all of this is pretty difficult to do for higher order ADCs, so there's some simple equations in your textbook that kind of highlight all this. So if you want to compute the digital output, you do the integer function. And depending on if you're using a calculator or Python or MATLAB, the integer function will either round down, it will truncate, which means it'll just remove the decimal point, or it will round up. Me personally, I don't really care because I'm not building an ADC. I just want to make sure I understand it. And so if you plug this in Python and you use the integer function and it rounds down or it rounds up or it truncates, it really doesn't matter. For higher order ADCs, you're really just in the noise, in my opinion. So you do the integer function of the input voltage minus VR lower, the lower range, which in this case is 0, divided by VR upper, which is 5, minus VR lower, which is 0, times 2 to the n. And so in this case, you would get, for this example, you would get 0.88 minus 0. So it'd be 0.88 divided by 5, which is, I don't know, it's less than a fifth. It's like 0.2. Then you would do 0.2 times 4, which would be 0.8. And depending on your integer function, you would either round down, so you would get 0, or if you round it up, you would get 1. And it's interesting to take a look at this. What you're doing with these bins is you're taking 0, 1.25, 2.5, and 3.75 as your bins. You could easily make 1.25, 2.5, 3.75, and 5 as your bins. You could take the upper limit or the lower limit. It just depends on how the ADC is offset. Okay? The error in your computation is going to be your input voltage minus that digital output, which you just computed, times that range, that bin width that we computed here. So in this case, it would be 0.88 minus 0 times that 1.25, and you would get an error of 0.88. And that would tell you your error between your input voltage and your converted signal. Now the last thing, where's my stool? The last thing that I did was draw this simple A/D circuit. This is by no means an accurate circuit model, but it gives you an idea of how ADCs work in real life. If you remember in the last video I posted a video on integrating op-amps. And so what you can do is you can apply a reference signal to an integrating op-amp. And if you apply a reference signal to an integrating op-amp, it will integrate at a constant slope. And so what you can do is you can take this output voltage and you can run it through a comparator where the top portion is the output of that integrating op-amp, and then your input voltage that you're trying to convert to a digital output. Well, if you plot those two signals on a voltage on the y-axis and time on the x-axis, the input voltage here is going to be constant, right? Because that's the input voltage that you're getting. The output voltage of your integrating op-amp is going to jump in discrete jumps every time you run through a clock cycle. So every time your CPU goes through a clock cycle, your integrating op-amp is going to jump up a level. And every time it's going to jump up a level, you can run it, you can check the comparator and say, is my output voltage greater than my input voltage? Once your output voltage is bigger than your input voltage, the comparator is going to tell the clock, hey, stop counting, right? Every time you do a CPU cycle, you store the clock. You tell the user, hey, that's your digital output, right? So this input voltage can change up and down, and then the number of clock cycles required to become greater than that input voltage essentially becomes your digital output. And this is a very, very easy way to make a A/D circuit. It's very slow. I say very slow. Clock cycles are like megahertz now. Well, gigahertz depending on what kind of computer you are. But there are ways to like parallelize your analog to digital conversion now. But I just wanted to give you just a quick example of how that works. Okay. And so this is a very, very quick example on how computers store information using bits, the difference between analog and digital signals, bits and how they work in powers of 2 and the number of possibilities that come from there, and then how to take an analog signal and convert it to a digital output, and then that digital output and convert it to your digital signal, and then also computing the error associated with that. And then finally, a simple circuit that sort of shows you what that circuit could look like. So in the next video, I'm going to show you the really quick and simple way to convert a decimal number to binary. And because here's the thing, this number 0, 1, 2, and 3, a computer can't store the number 3. It can't store 3.75. You still need a way to convert these to bits. And that's what I'm going to show you in the next video. So stick around and I'll see you then.